Welcome to the Inside Line podcast presented by Thor. This is another tech edition where we talk about modifying a cylinder head. So we went to Race Tech and grabbed Andrew Flores, their main engine guy, to talk all about it. We started with what a cylinder head is, kind of the anatomy, all the different parts, how they all work together, and then we move on from there into what Race Tech does, or pretty much any engine shop does, when they get an OEM head and find the strengths and weaknesses and what they can do to modify it. There's a surprising amount of testing that goes into this, and it's not just making things bigger. I mean, a lot of people just think porting, you just go in with a grinder, you make everything bigger. Bigger means more flow means more power. And it is so much more complicated than that. I think Andrew does an excellent job of explaining all the different things that are going into head modifications and ultimately what the finished product is. At the end of the day, I hope you guys walk away with a better working knowledge of what is going into head modifications and how at the bigger picture of your finished motorcycle with exhaust and cams and race fuel, ECU and pistons, how this all fits together, and you can make better decisions on how you want to spend your money on your engine, because each one is a little bit different. Sometimes you just really don't need as much work as you think you do, while others you need different work than you think. And it's pretty interesting how this all comes together. So before we get into the podcast, we have some sponsors to thank for being part of the Inside Line. First is Thor. Since 1968, Thor MX has elevated motocross racewear innovation to new heights. Designed and fabricated to the standards set by a long list of Supercross and motocross champions, the Thor 2020 collection features all new performance-driven racewear, boots, helmets, and more. Go to thormx.com or visit your local Parts Unlimited dealer to learn more. Next, we'd like to thank Maxxis. Maxxis Tires is proud to introduce the all-new Max Cross MX ST, a premier motocross tire tested and developed by the King, Jeremy McGrath. Available now at your local dealer. Also, we'd like to thank Chaparral. From tubes to tires, MX jerseys, gear bags, hard parts, and a huge selection of dirt bikes, Chaparral Motorsports has everything you need to keep you roosting the track or the trail. Check out chapmoto.com. We are here with Andrew Flores from Race Tech, and we're going to talk about heads today and kind of engine modifications in that direction. So maybe start with a little bit about you and your background in working with engines.
Alrighty, so I've been doing this for about 10 years now, and definitely didn't wake up and just know all the answers. I've been pretty fortunate to have some really great mentors throughout my career. Started out with Jim Wood. He really specialized in flat track engines. And with those engines, it's, high horsepower. So, I started with him really not knowing anything about engines, and it was really cool to kind of evolve with him and start doing a lot of the engine modifications. From there, I came to Race Tech about 5 years ago and was mentored by Paul Thied, Rob Brown, Darren Morgan. Rob Brown was pretty fortunate to be mentored by a ton of guys. Some of them being, Brian Truesdale, Guy Oler, Darren Morgan, and Joe Mondello. So these are some pretty credible guys in the automotive industry.
Yeah.
And it was really cool to kind of do that. And these guys have been able to progress my career so far to the point that I never thought I'd get to on my own, and I wouldn't be where I'm at right now if it wasn't for those guys. So definitely gotta give a shout out for them for getting me where I'm at.
Yeah, that's pretty cool. So coming to Race Tech, how long has Race Tech, the engine department, been working?
So Paul Thied actually started with engines, and after that he kind of got into the suspension side and got super heavy into development with suspension. But yeah, a lot of people don't know that he started doing engines. That was his first passion. So kind of went away for the engine program for him, and then about 5 years ago we started it back up, and our goal was to never do full engine builds. It was to be a resource of research and development for all the tuners, all of our Race Tech centers, all of our dealers, and really anybody that was trying to build an engine. So
it's, would it be fair to say it's almost like kind of an R&D department, and then you can give that info to everyone that you guys work with and is race tech centers?
Yeah, exactly. We want to work with everybody. We're not here to be anyone's competition. We want to be, everyone's source to be able to work together. We have a ton of equipment here, and we're pretty fortunate to have it. And we want to be able to provide everyone with, quality engine machining services to build a good quality engine that performs well.
Mm-hmm.
So whether you're looking for the standard rebuild or some performance stuff, there's so many different options that we can do.
Yeah. Well, let's get into what we can do. Basically, I think starting off with kind of the anatomy of a four-stroke motocross head so that everyone's on the same page and understands what we're talking about. So maybe run through, all the parts that are, when you're looking at a head, what's in there?
So looking at a motorcycle head, there's so many different variables there. The cylinder head is the key to any engine. It's basically the brain. And without a good cylinder head, you're not going to have a good running engine.
Right.
So in the cylinder head, you got, camshafts, your intake, exhaust cam, you have valves, valve springs, you have, your intake track, you have your valve seat angles, your valve angles. You kind of want to start looking at all those things and see what we can achieve by modifying them if we want to modify certain things. Kind of goes back to what's the bike going to be used for. So
yeah, so like starting, whatever your end goal is, like if you're a Supercross guy or motocross guy or flat track or whatever, off-road guy, then you start with the end goal and then work backwards from there.
Yeah, so whatever application of riding you're doing, that's going to be, our end goal. So for Supercross, they're using a different power characteristic than, motocross would be, or flat track or hill climb. So once we find out what the engine's going to be used for, that's when we kind of start approaching, what route we want to go. That's going to give us the best performance for the amount of money that you want to spend.
Right. So I think a lot of people, there's people out there that know exactly what polishing and porting a head means. I think there's a population that think they know what it means and are kind of guessing. And then obviously there's newcomers to the sport that have no idea what that means and would like to know if that's something they need to do to their bike. So it's kind of thrown around a lot. But what specifically does that mean to say, okay, I'm going to get my head polished and ported?
So that's a great question. I really wish that the word porting and polishing kind of went away.
Okay.
Because you have porting and polishing you definitely never want to do to an engine.
Okay.
It's really bad. You want it to look really cool and really pretty and shiny, and that's what people want to see.
Mm-hmm.
But the truth of it is polishing and intake port is probably the worst thing you could possibly do.
And why is it?
Because it causes the fuel to come out of atomization, or it's not suspended. So you basically get fuel puddling. As soon as you turn a fuel from a vapor into a solid's not compressible anymore. So you're going to start getting puddling of the fuel going into the combustion chamber, and you're going to have a really inefficient cylinder head. So back to the original question, porting and polishing, typically you start with just cleaning up the cylinder head. Mm-hmm. And that's kind of the key to unlocking some horsepower is the more you can get that cylinder head to flow, the more horsepower you're going to make, which there's a lot of different variables to that. Right. Bigger is not always better. Right. And most of the time, you got a bigger hole, you're flowing more horsepower, or you're flowing more air, you're going to make more horsepower. And that's definitely not the case. So,
right. So there's a lot that goes into it. It's not just make the intake track and exhaust as big as possible. That's not, because it's like we talked about before, it's velocity, it's speed of the air and the fuel mixture.
Exactly. So you have air quantity and you have air quality.
Okay.
And it's not always about the air quantity that you can get through there. You have CFM and you have velocity.
What's CFM?
CFM is cubic feet per minute. So how much air you can get to flow through that cylinder head.
Okay.
So you want to be able to get that cylinder head to flow an adequate amount of airflow while sustaining velocity. And those are the two keys to the cylinder head. So if you can get more airflow without losing velocity, you're going to gain horsepower. Or if you can get more velocity without losing airflow, you're going to gain power as well. And velocity is torque. So the more velocity you can have, the more torque you're going to get. And that's what our goal is on a 250 engine. But you can also have too much velocity. So you got to be careful with where you're going with that stuff, because you can get so caught up in airspeeds that you don't realize you're breaking boundary layers and you start reverting. And at that point, you start kind of fumbling over yourself and the bike doesn't make power anymore.
So looking at, I mean, I don't know, I've seen, you know, different engine builders put videos up and they're just basically trying to open everything up. So when you make the intake track bigger, what is happening there?
You're increasing airflow, but anytime you make any area bigger, you're losing airspeed.
So it slows down.
So it slows down.
Okay.
Exactly. And you want to be able to keep airspeed up as high as you can, because that's where all your power is going to come from. That's how we're able to get our compression ratios as high as we are while running a low octane fuel. So an efficient cylinder head, you're really able to do whatever you'd like, you know, as far as, you know, fuel compression ratio really livens up the engine. So I think we keep getting a little off topic here, but, you know, porting a cylinder head was originated to be able to squeeze more horsepower out of your engine. It's just kind of how you approach it, which we can get into later, how to get that horsepower. And bigger is not always better.
We can stick with intake track and exhaust, or if you want to talk about valves now, I mean, however you want to dive into kind of, you know, because I eventually want to talk about starting with an OEM head. Maybe that's a good way to illustrate what all you do, because, you know, every year new bikes come out, they have different designs. I mean, not every year, but there are new designs that come out. You take those off the bike, you look at them, you see what they're doing, and then you go from there.
Definitely. So we can kind of talk about where we start, you know, when we first get a new bike in, you know, 2020, for example. A lot of these bikes are changing. Every year they're making different changes to these bikes.
Right.
Sometimes it's not always the best changes either. A lot of these OEMs are kind of shooting for a high horsepower number, and they're forgetting about, you know, the rest of the power characteristic. Low end, mid-range, what the bike's doing at half throttle, what it's doing at a quarter throttle. Most of the time you're doing these dyno runs at 100% throttle. And that's cool and all, but how often is the rider at 100% throttle?
Right. I mean, other than pros.
Yeah, exactly.
But even most pros aren't always wide open.
Exactly. And, you know, the motorcycle guys, we're working with a pretty rare breed of an engine, because most engine developers, they tune an engine for a specific RPM. You know, Pro Stock or dragsters are a perfect example for that. They tune their engine for exactly what RPM they're going to be running at, and that's where they stay. On a motocross or supercross bike, we're working with going from, you know, 4,000 RPM all the way up to 14,000 RPM. So we have a range of 10,000 right there. Right. And to be able to make the engine run good through each particular RPM is pretty hard to do. So that goes back to where we want to make horsepower and what the bike is going to be used for. So typically we start with dynoing the bike. We have air fuel ratio hooked up to it. We do 100% throttle run, and we do some partial throttle runs as well. And after that, we tear the whole thing down. We blueprint the entire engine. We spec everything. We write all these numbers down. We put the head on the flow bench. We measured the flow at every 50 thousandths valve lift. And then after that, we velocity or port map the cylinder head. And what that means is we go into the cylinder head with a velocity probe, and we see what the airspeed is.
And so you're putting a kind of a finite point at different spots in the head to be able to tell how fast in that exact spot airflow is going.
After that, we typically port mold the stock port, so this way we can scan it, have it on the computer, really analyze what the air is doing. We measure intake, track runner lengths. We measure cross-sectional areas. We're seeing what the throat percentage is, what the piston speed is, the bore, the stroke. valve size. I don't know if I said valve size yet, and where the engine's going to be operating as far as the RPM. So it's not just one particular thing that we're looking at. We got to look at all these variables to see exactly what we can do and what we can't do. Because one engine, we can do a lot of working on a certain area, and other engines, we can't even touch that area because we're going to ruin it.
So using that as an example, it's almost like if something, already comes with an intake track that is maybe your data shows is maybe already too big. It's flowing a lot of air, but too slowly, then you don't want to start opening that up and make it worse. It's like, so is there a way to go the other way? Add material to basically make something some diameter smaller, but move the air faster.
Yeah, definitely. So there's a couple different ways we can go about it, and ultimately we can do whatever we would like to the cylinder head. It's just kind of comes down to budget and how much time do we have.
Okay.
So what we want to do is on the cylinder heads that flow a lot of air but don't flow it very fast, we want to add material. So we can either weld it up, or we have some pretty crazy industrial strength epoxy, and the stuff was invented to plug holes in submarines. So
Okay.
It's pretty crazy stuff. We've never had a failure with this either, so that's really cool.
And when you say welding, you're just going in and adding material?
Yeah, we'll weld or we'll add epoxy.
Okay.
So epoxy is a really good way to do this for rapid prototyping, and we can also run that on the engine and not have any problems with it either.
Mm-hmm.
So when we're adding this material, I typically add quite a bit to it, and then we start flowing it and seeing what the velocities are doing and what the airflow is doing. So like I said earlier, you want to be able to have a lot of CFM while sustaining airspeed, or vice versa.
Mm-hmm.
And when we're doing that stuff, we start kind of manipulating the shape. We're measuring cross-sectional area again. We're measuring intake runners, your converging angles, and looking at the seat area because that's a tuned venturi right there. And what a venturi does, for everybody that doesn't know, we're creating an area where converging and diverging air can create a vacuum.
Okay.
And the vacuum is called a Bernoulli effect. So high velocity air creates a low pressure vacuum. How can we create the best tuned venturi we can at that valve seat to be able to pull as much air through that area as possible?
Okay.
So what we do at the valve seat, creating that tuned venturi, affects the entire runner behind that. So what we do up front affects the rear of the port.
Okay, well, now we're starting to talk a little bit about valves. So, looking at the valves, what are the options and the valves and valve seats? What are you guys doing? Obviously, there's valve jobs. They've been around for a while. So what are the differences between like a 3-angle or a 5-angle or what's happening there?
Yeah, awesome question. So a standard 3-angle valve job, you're going to be getting 3 angles on your valve seat. Typically, it's a 60, 45, and a 30-degree angle. Comes standard on pretty much every cylinder head. Once we kind of figured out you wanted to be adding more angles and more radius to that valve seat to increase airflow, we started developing cutters. And we have separate cutters for almost each particular cylinder head that we're working with. Again, kind of goes down to application that we're trying to achieve.
Mm-hmm.
And we have different lengths of these angles. We have a wide range of cutters to kind of increase the airflow. So whenever we're adding more angles, we're increasing airflow.
Because
that's the goal.
You're making things smoother. You're making a radius smoother.
Essentially, yeah. We're giving the air more time to turn. So when that valve starts to crack open, we're able to increase airflow with adding more angles there at the valve seat.
Okay. Are there examples where you look at an engine head and you want to start, where do you start at the valve angles? You start manipulating that, or do you start with, the intake, or do you start with the exhaust, or where is the point of kind of putting all these things together? Where do you start?
Well, we start on the dyno, we start on the flow bench, and once we get that data, we can kind of see what the bike's lacking and what it's not lacking.
Okay, so you go back from like, this needs more of X, so we're going to start here.
Yeah, so some of these engines are lacking bottom end.
Okay.
And so we go through all these different steps. We have a wide range of tools that we use, including some proprietary engine simulation software that was provided by Darren Morgan. Some really cool stuff that he's provided us. We go in there and it's like, okay, are we lacking bottom end? We look at the dyno chart, and a dyno chart is, you can see different wave amplitudes. Mm-hmm. And is that dyno chart going into a negative wave amplitude, or is it a positive wave amplitude? And do we want that negative to be a positive, or vice versa? And at that point, we start looking at the cylinder head. We're looking at our air speeds. We're looking at our flow numbers. And if we're trying to get more bottom and mid-range, we're going to be chasing velocity, not particularly CFM. So we definitely start with the intake runner. We look at what we can change there. And we look at, the seat area and the valve shape, the valve size. After that, we start seeing what angles we can kind of manipulate. So a lot of times we're trying to make the air do something it's not supposed to. Air doesn't like to turn, mm-hmm. and we have to make it turn.
Right.
So how can we achieve that? Typically, it's going to be with a valve job and, a different seat.
So just so we can all visualize it, a 90-degree angle, a sharp edge, air is not going to whip around that corner smoothly.
Absolutely not.
No, it doesn't want to do that.
It doesn't want to do that.
And does that create eddies and stuff, just like?
Yeah, it'll create turbulence. Mm-hmm. And in some cases, we got into wet flow a few years back. And okay. when we did that, we were able to visually see what this engine was doing.
And wet flow is using a flow bench, but putting dye in it.
Yeah, we're sucking dye through the cylinder head while we're running these tests. And we're cool. reading what this dye is doing and where it's going. And in some cases...
So you can see where it's pooling or where it's sticking or whatever?
Yeah, definitely. So sometimes the air is going backwards. And you're like, what? How's this even possible, It should be going through that hole. But, we have a dead area, or we have an area where the air can't turn, and it's going back into the cylinder head. So it's like, how do we fix that? Okay. And that's probably something I should have brought up earlier is, we do wet flow testing. Mm-hmm. And before we do anything, we look at what that engine's doing, or I should say what that air is doing. And once we see some problems there, we start kind of approaching it and how can we make this better?
That'll give you the exact visual, reference to say, okay, if it's pooling here, we either have to add or remove material here or change this angle or anything like that to get everything to flow.
Exactly. And it's pretty tough because no cylinder head's really the same. Mm-hmm. And all of them are doing something different, and it's like, how can we make all of these things work?
Right.
So, and at that point, if there is, a lack of bottom end and we have reversion, we're like, okay, we need to boost velocities. We can't be having this air go back into the intake port.
Right.
So typically we're going to start with intake track, air velocity, CFM, and then start changing angles until it starts getting better. So we make baby steps, mm-hmm. take some baby steps, put it back on the flow bench, and go back and forth. And, the flow bench has kind of been one of those things where a lot of people kind of hate on it. And it's like they think it's worthless because they do all this development on the flow bench and then they put it on the dyno and it doesn't work. Or the rider rides the bike and it doesn't work. And
when you say it doesn't work, the rider doesn't like it or doesn't like the way the power is.
Yeah, exactly. And it's like, man, the flow bench said we made all these flow gains. And I got to agree with them. Yeah, the flow bench could be a complete waste of time if you don't have the proper fixturing.
Right. So earlier you were showing me all the different ways that you put the head on and the fixture. So talk a little bit about that and how that, makes the flow bench work, basically.
Okay. So whenever we're flowing a cylinder head or doing any kind of data testing or anything, we got to eliminate as many variables as we can. And one of those would be the same bore and stroke. We have the cylinder head on this machine that's pulling air. It's a machine. We're telling it what to do. We can start flowing this thing and putting the head in different areas of this hole that air is sucking through, and we're going to get different results. We can radius off the beginning of the runner, and we're going to get different results. So we start with fixturing. Let's eliminate all these variables that we can inflict and make sure that we get consistent readings every single time. So we have a range of different flow bench fixtures. I mean, you saw them, we have a ton of them.
Mm-hmm.
And it's the exact same bore, the same stroke. So we're simulating exactly what this cylinder head's going to see. We also have a radius inlet because we don't want to change that. We want to be seeing what we're changing in the port, not what we can, change on the radius of the beginning of the intake port.
And it's almost like the radius inlet is kind of best case scenario.
Yeah, exactly. But we're starting and finishing with the exact same fixturing. Okay. So that's not a variable.
Right.
We're able to see exactly what we changed. And, some cases we go backwards. I mean, this R&D process is brutal.
Yeah.
And it's like we were working with Chris Blosa a few years back on the 2018 Honda. That was a new engine. And I mean, I think I had 30 different iterations of this thing before we found something that worked. It was literally like, throw it on the flow bench, throw it on the dyno, let Chris ride it. And we got to make all that data kind of talk to each other.
Right.
And sometimes it's not the fun part of the job.
No, doesn't sound like it.
Yeah. 30 different combinations.
Right.
It takes a lot of time.
So we've talked a lot about the intake. What else? Are there different considerations when you start to look at the exhaust port and that tract going out and the different things that work inside there versus the intake?
Yeah, definitely. So you have an intake track, a combustion chamber, and you have the exhaust port.
Right.
And all of them work together. The combustion chamber is just an extension of the intake track, and it's also the beginning of the exhaust port.
Okay. That's a good way to look at it.
Yeah, you have your converging air coming through the intake port. Then you have your diverging air, which is coming out of the exhaust valve into the cylinder, into the combustion chamber. You want to be able to control that air. So we got to work a lot with the combustion chamber, both for the intake and exhaust side. So on the exhaust side, the flow bench is we can't do as much real world testing on the flow bench on the exhaust side because we're not seeing that pressure that we would see in a real world application.
Okay.
When that exhaust port's opening up or those exhaust valves are opening up, we have so much energy built up from that combustion process that we can't simulate that.
Right.
But any data is better than no data. And once we figured that out and, we started doing a lot more dyno testing and looking at the cross-sectional areas of the exhaust port, we do pretty much the same thing that we would do on the intake port on the exhaust side. We don't approach it the same way, or I shouldn't say that. We approach it the same way as far as looking at, the runner length, the cross-sectional area, the velocities, along with the throw percentage of, the seat ring. And once we start manipulating that stuff, we see what it does in the real world testing because the flow bench isn't a good indicator for that stuff. But we like to have some data on that. And, every day we're progressing as far as how we can, correlate this flow bench data to the real world testing.
So you were showing me, I think it was the CRF 250R head that you were talking about the exhaust. It's over exhausted. I hadn't heard that phrase before.
Yeah.
So explain what that is and if you're seeing more heads that are like that.
So as of right now, they're kind of the only ones that have the dual exhaust, and It's a big area. I mean, when you add both of those areas together, it's massive. Mm-hmm. And that was a problem for us in the beginning. We were like, man, how can we fix this? So we tried different things. First started off by, blueprinting everything, measuring it all, putting it through some simulation softwares on the computer. And the thing needed increased velocity. It had so much flow, but it didn't have the speed that it needed. So we tried welding the thing up. We tried so many different iterations on that thing, and we actually had to shrink that thing up pretty good size. But it started getting expensive. So what we did was, how can we trick this port into believing that it's smaller than it actually is? So we started screwing with valve angles and seat angles and throw percentages. Mm-hmm. And that particular head runs a completely different setup than we would on any other cylinder head.
Okay. So you changed basically the valve seats to make them smaller or?
Yeah, we changed the valve seats and made them smaller. And almost a lot of these cylinder heads now, we're having to change the exhaust seat. And the reason we're changing the exhaust seats is that we need more area to work with than the factory's giving us. So we need to be able to make that air turn, and it's really hard to add material into something, so we have to start fresh and start manipulating the stuff. So a lot of our heads are coming with seats now because we have to have that area of material to be able to make it do what we want it to do.
So a lot of this testing and a lot of the work that you're doing is here, obviously, in the shop. Um, have when you start to combine that with dyno and then real world testing, do you ever see any discrepancies where it flows really good, the dyno looks really good, all your numbers look great, and then you give it to a pro rider, he goes and rides it and says, I don't like it?
Fortunately, we haven't had that, and we've chosen a lot of this equipment for that reason.
Okay.
And a lot of the testing that we do, we're able to eliminate that problem. So one being is we're super heavy on velocity probing. We're checking what this airspeed is along with the flow. We're checking these low lift numbers. We're checking the high lift numbers. We're checking partial throttle on the dyno. We're checking full throttle on the dyno, because you could have an engine combination that runs really well at 100% throttle through the entire power curve, meaning, lower RPMs, mid RPMs, high RPMs.
Wide open.
Wide open.
Yeah.
But what does that engine do at 50% throttle or
Right.
20% throttle or any other throttle that you'd really want to test? And something that works really well at 100% throttle doesn't work at all on a partial throttle run. So we've had that. We've done testing where our bike runs really good at 100% throttle, but it doesn't run very good at 50% throttle. So we have to address that, and that's why we do so much testing. And we're able to put all of these pieces together so that when the rider gets it, he's happy.
So talking a little bit about riders, what pro riders have you worked with or are currently working with that you can talk about, and kind of the feedback that you get from them and how you guys make the changes? Maybe sometimes it all works out really well and he likes it, but he wants something different.
So we work with a handful of racers. Most of them are around the globe, but we're not working directly with the racers. We're working with their teams or the mechanics. That's kind of our goal. If we are working directly with a racer, it's some small mapping changes. And if the rider does have any complaints, we usually listen to his complaints before we start doing all this stuff. So this way we can kind of achieve a proper power characteristic that we're looking for that rider.
Right.
And most of the time, a lot of these riders have the exact same complaint, depending on what manufacturer bike they're riding. Yeah, exactly. So some of these bikes are making really good top end power, but not a lot of bottom end, and all these guys want a ton of bottom end out of their motorcycles. So as long as we can achieve that, they're usually pretty happy. If they do want some changes, we always go back to the drawing board, figure out what we can change. There's always options for these guys. But we're always working with the riders, mechanics, or the teams.
So have you ever come across a head that's kind of like, has really good numbers, from the factory, and it's almost like there's not much to change? Or is it always like, oh, okay, I can see exactly where we can make major gains?
Yeah, there's a few little key areas that we find that usually always make gains, but it's getting harder and harder to find these gains in these cylinder heads. I mean, all of these bikes coming from the factory are actually really, really good. Mm-hmm. And they're doing a really good job at making our job hard. And it's also kind of fun because it's like, man, they're making it challenging. So there are some heads that we don't do a lot of work to. And one of those heads are, KTM. Mm-hmm. You don't want to do a lot of work to that. I mean, the bike runs really well. That's one of our heads that we add some material in there to boost some velocity for Supercross. Mm-hmm. And we've had really good results. But, I mean, that's a really good head. And all of them are progressively getting better and better. Every single year they're getting better and better. It's just goes back to application. What are these guys looking for? Mm-hmm. Are you looking for a peak horsepower number? Or are you looking for, better broad range characteristic of bottom and mid-range power?
Are there different considerations for 250 versus 350 versus 450?
Oh, yeah, big time. So 450, I mean, those things already have so much power. So
right.
It's how can we make that power smoother, better, more progressive, not have such a hard hit? And it's a completely different application than a 250, because 250, we want that thing to hit as hard as possible, along with have a high horsepower, because it's what they lack. And we definitely take a different approach on the 450 versus the 250 or even the 350. But it all comes down to what that rider's looking to get out of it. if that guy wants his bike to hit really hard, we're going to make it do that. But you got to also keep into consideration that if you want a lot of bottom end power, you might not necessarily gain a ton of top end power, but you're not going to lose any. And it goes hand in hand. You can't have everything.
Right. We touched on fuel atomization a little bit, but when you're looking at a head, and I remember there were some things in the forum, some photos of the, I think it was the Honda Works edition that said it was ported and polished, or I don't remember exactly the wording, but they were showing photos and they're like, oh, this doesn't look polished, but that, like you said, you don't want that. So maybe talk a little bit about having texture in intake. Is that what gives it fuel atomization, or?
There's a lot that goes into fuel atomization. One of them is it's pretty easy with the fuel injector now. I mean, the thing's coming out as a vapor. Okay. And you want to have a really rough intake port so you have a better boundary layer. And
so what is a boundary layer?
Basically the layer between the port wall and where all the fuel's at. Okay. So you never want to have this fuel actually sticking to the walls. You want to have that stuff suspended going through the cylinder head.
So would it be analogous with like a golf ball, basically, that it kind of has its little boundary? I mean, the air isn't actually touching the ball. It's kind of touching the air between the ball and the air.
Essentially, yeah, that's actually a really great thing that you brought up. So people tried doing that to intake ports. They started making a golf ball shape with CNC porting. We can get into CNC porting in a little bit too, because there's a lot of misconceptions to that. But essentially, if you put a golf ball shape in a port, you're creating little vortexes in every single one of those pockets, and you're pulling that fuel from suspension and making it puddle.
Okay,
so deliberately doing that.
Yeah, that's really bad.
On the flow bench, though, you're going to see gains, and that's another thing too. Where you can get lost in CFM numbers on the flow bench, and what happens on the flow bench doesn't work in the real world application. And that golf ball effect is a great theory behind that.
So right now, when the optimal intake track, like texture, I guess, or finish is, would you call it rough? I mean, what is? Yeah,
it's rough. And truthfully, I wish we could make it rougher. We want that thing to be as rough as we possibly can while still making it look good. And truthfully, the ugliest runner or port is going to be the best performing one. You don't want the shiniest one. And that goes back to fuel atomization. You want that fuel to stay atomized all the way until it gets into the cylinder. The more atomized that fuel is, the better combustion you're going to get. So how can we achieve that? And it's with a rough intake runner.
Yeah. Lately some of the bikes have come with dual injectors. I mean, does that matter at all, or is this all, everything happening, in the throttle body is, it doesn't affect what you guys are doing?
Definitely. So the dual injector, the theory behind that is to inertia charge that intake. And the further you can put that injector, the more time you have for that speed to increase. Okay. So the goal there is to get more top end. You're going to have all this airspeed coming through the intake runner, and you put this injector way in the back, and it has more time to increase velocity as long as your intake track is the shape it needs to be, as long as you have that airspeed to pull that fuel. So if you don't have the airspeed, you're not going to pull that fuel from way back in the beginning of the plenum or the airbox.
Yeah, so with those particular bikes, that is a consideration that you guys are taking.
Yeah, definitely, but it's what are you trying to achieve? Is it worth the money that you're going to spend to put this dual injector in your bike? Most of the time, not really, from what we're seeing. Right. And it comes down to what is the bike going to be used for? Because a second injector, you're typically going to see your gains at higher RPM.
You wanted to circle back to, what was it, CNC devalving, or what was it?
Yeah, CNC porting. So a CNC machine is a copier. So whatever you put in that machine, it's going to spit out. And if you don't start with a good port shape, then you're not going to get a good port shape once it leaves that machine. So most of the time, you have to start with a hand blended cylinder head before you can even start with going through the CNC process. And most of the time, the CNC won't touch every part of the cylinder head, and people are paying for the CNC they want CNC look all the way through. By the time you get that CNC look all the way through, you've opened up the port so much that you've ruined the cylinder head. And most of the time you got to go back and hand finish it. So the CNC porting isn't always the good route. And, everyone's like, it's CNC'd, it's CNC'd. It's like, okay, well, what did it start with? I mean, regardless, you got to have that thing, you got to go through testing. Just because the cylinder head was CNC ported doesn't mean it's going to perform well.
Right. Well, I mean, I think that goes back to, got people just having the notion of porting means just open everything up. Just make it bigger.
Yeah, you don't want to go in there with your porting tool and just start making giant holes, because it's definitely not what you're going to be looking for.
Right. So kind of OEMs are, with a lot of motocross bikes, and some of the big changes that they're making every year is, getting that intake track straighter and straighter. Is that something that eventually that you see is you can't get it any straighter, or does that make it more of a challenge for you to make everything flow better, because they're flowing pretty well?
Yeah, these heads are flowing really well these days, and they are getting straighter and straighter. And that's the goal. Air doesn't like to turn, like Ed said earlier. Mm-hmm. So the straighter you can make that intake port, the better volumetric efficiency you're going to end up getting from that particular cylinder head, better charge.
I mean, at some point there's only limited amount of space and angles and stuff, so there's only going to be so straight, I guess. So maybe even talking about looking at the Yamaha with the intake on the front of the engine and a whole different setup there. In your opinion, would you say that that's kind of a good design from intake, standpoint?
Yeah, I think it's great. I mean, they're really trying to get that ram effect with that particular setup, and that's what we're trying to achieve on any cylinder head, is how can we get that air into the cylinder? How can we fill that cylinder quicker, more efficiently? And Yamaha, let's turn the engine around. Let's put an inertia supercharger basically on that thing, and it works.
So explain the ram effect a little bit.
So the ram effect is forcing air into the intake port rather than, whenever you're filling a cylinder, you're changing, when the piston's at the very bottom of the cylinder, you have a difference in pressure, and whatever the ambient pressure is outside is going to fill that port. So we have to try to inertia ram that as hard as possible. Try to get that air packed into that cylinder as quickly as we can. When we have help from air coming from the front of the engine, pushing air into that intake port, it definitely helps.
Okay. Yeah, that makes sense. What, some people are decking their heads, and what exactly does that mean? And is that something that you guys do?
Yeah, that is something we do. And that goes back to, one of my mentors, Darren Morgan. He showed me some really cool things about why you don't want to deck a cylinder head. And that brings us to combustion chamber shape, like we were talking about earlier.
Yeah.
Combustion chamber is the continuation of the intake port and the beginning of the exhaust port. Mm-hmm. When you start taking material away from that cylinder head, you're compromising those angles, and you're not giving that air enough time to kind of come back or start.
Okay, so I mean, the theory behind that is if you remove material, you're making that the combustion chamber smaller, therefore the compression is going to be higher, there's going to be more energy. But what's not taken into consideration, if I'm understanding correctly, is, the engine, the valve angles were not designed for that new, that decked head, basically.
Exactly. So you start taking away flow, you start compromising flow as soon as you start taking material away from those angles, because the combustion chamber is really important to an intake and exhaust. So instead of decking a cylinder head, we start decking the cylinders, because there's nothing to compromise there.
Right.
Not only that, we're able to get more area out of decking a cylinder than you would out of decking a cylinder head. You're taking away chamber. A chamber's not perfectly round. It's all kinds of different shapes, and there's different angles there too. So we deck a cylinder, and we're able to kind of calculate how much compression ratio we're going to gain by doing that.
So what is the difference between decking a cylinder and getting a high compression piston?
Essentially...
I mean, like the end result.
The end result is going to be somewhere near the same, depending on what you're trying to achieve. When you're looking at a piston, you're looking at, the pocket depths, you're looking at the dome shape. And sometimes the crazier the dome shape, you're not going to get as good a performance because the air is all screwed up in that cylinder, and you're creating turbulence, and the thing won't work very well. So it's like, how can we get the most compression out of a piston shape that's efficient, and then we have some room in the cylinder that we can deck a little bit and gain that compression back. So typically, you don't want to throw the highest compression piston you possibly can in there because you're going to start screwing up the dome shape.
Right.
And once we get a dome shape that's working really well, if there's room to deck the cylinder, we will do so. And what that does is kind of tightens up the squish area, and we get a better combustion.
So looking at all of these puzzle pieces, I mean, there's a lot of different areas that can be changed and a lot of different things going on. How would you say that this fits into, just a normal guy that has a bike, he wants to make it work better, maybe races on the weekend or whatever. He plans to build a whole dirt bike. There's all the different things. So there's exhaust, there's different cams, there's race fuel, there's ECU changes, there's all of those things. So at what point in the process would your suggestion be for like head modifications? Do you start there? Do you put it in the middle, or do you finish with it? When you're looking at the whole engine package.
Yeah, so the whole engine package, that's really where the automotive industry outshines the motorcycle industry, because the automotive guys, these engine developers, are making all of these components work together. Where on the motorcycle side, they are kind of piecing this thing together with whatever they can get for the best price and whatever logo looks the best. Right. And sometimes all of these components that they put on there really hurt the engine. So we always start with a good running cylinder head, or a good flowing, efficient cylinder head. And after that, we will make recommendations on cam, piston, exhaust, ECU, fuel. But it's not, you got to be careful with what components you put with what. So we'll make our recommendations, but the goal is, as long as you have an efficient cylinder head, you're going to be okay.
So basically, it's a good place to start, rather than because I guess if you're looking at your budget, I guess it's all budget dependent, really.
Yeah, exactly. So, budget and application. What are you trying to achieve? I mean, I can't go back to that enough. It's not what can we do, what do you want? Because we can make this stuff do whatever you'd like. And we've ran into cases where we develop a cylinder head that we want to spool up really slowly and make a smooth linear power curve. And then once we do that, the customer goes and puts, a ginormous cam in the thing and tries to achieve the exact same thing that we did. And at that point, they start working against each other. Right. And the bike doesn't work, or the engine doesn't work. So what are you trying to achieve, and how can we help you get there?
So every time you guys do a dyno run after, trying to get the optimal working head, are you using the stock exhaust?
We'll start there. Yes.
Okay.
Yeah. And, we'll run different exhausts in testing and see what they do. And then we'll do what we do to the cylinder head. We develop some parts, some components, we throw it back on there, and we do the exact same tests. And typically, whatever that exhaust did on the stock engine, it'll do to our head as well.
So then once you say you have your head, modified by you guys, and then find an exhaust system that works well, and you want to get a different ECU, I mean, are they doing something different than they would with a stock bike, or are they saying, okay, what engine, mods did you do, and we're going to optimize the mapping for that?
Yeah, so once you have the bike on the dyno, that's really where you're going to start changing the mapping. So whenever you start changing all these components, the mapping is going to change. And that's where you start building your map. It's not necessarily like you have to have a specific map, because every component is going to start changing that mapping characteristic. And we do a ton of ECU mapping here. We work really closely with Vortex ECUs. We've really enjoyed their product, and the parameters that we're able to change on that thing are amazing compared to what other programs are out there. But when you're changing all these components, you definitely want to have a good map in there. And if you want to be running this bike, you just map it to where the bike's running good. I mean, sometimes you'll have, a certain component that lacks bottom end, and if that's what the customer wants, you just make the mapping work with that. And sometimes, if you want to lose power in certain areas, that's how the rider wants it, then that's what we do. And we do have to manipulate the mapping for that.
So like if I have, 2020 CRF 250R, and I say, okay, I want the race package that you've developed, but I also want a ECU that's mapped to match the changes that you made. Can I buy that from you at Racetech, or is that something that I have to go then take to someone else to remap?
Oh, gotcha. No, we develop a mapping for our combination of components.
Okay.
And you can get everything here. We'll supply you with the ECU, the map that we use that we've developed over the years, or for that particular bike. And we make all those recommendations for you. And it's like, hey, some of these dudes are sponsored by different piston companies, and that's the piston they're going to run.
Right.
So it's like, hey, man, this is the mapping that we've come to develop with our combination of components. You start changing things, it's going to be a variable there. And that comes down to, exhaust pipes, pretty much any component that you can throw out in that engine, it could compromise our horsepower.
So is there anything else that you think people misunderstand about, modifying an engine head?
Yeah, definitely. I mean, I would probably start with, as far as like modifying the cylinder head.
Yeah. Well, because people say, oh yeah, the engine mods. I mean,
engine mods. So you definitely don't take the advertised horsepower gains from each engine mod and add them together. That's not how it works.
Okay.
Another thing is octane is a pretty big misconception.
Okay.
The higher the octane doesn't mean the better the race fuel. You want to have the lowest amount of octane you possibly can before detonation. The more octane you have, the longer the burn rate. And it's not all about octane. And once you have a high oxygenated, level in your fuel, that's where you're going to start making power. So what we look for in fuel is what's heavy in specific gravity, because, we want to be using that kinetic energy. Object in motion stays in motion. So if we have a heavy fuel, if you have an efficient cylinder head or intake track that can pull that fuel, your volumetric efficiency is going to shoot up. We're packing that cylinder with more air because we have more weight behind it, pushing more
inertia, more momentum.
More inertia. So that goes back to inertia ramming. How can we ram that fuel and air mixture into that cylinder as efficient as possible? And it's with a heavy fuel, something that's high in oxygen, and something low in octane. So,
okay. So do you use at what point of the development process do you start throwing in different fuels, or is it you use 91 pump gas or whatever?
We'll start with 91 pump for all of our stuff, and that gives us, it's a good base point. Okay. You want to be comparing apples to apples. Yeah. You don't want to start with pump fuel and make all these changes to your engine or your cylinder head or whatever component you're modifying, and then put it back on the dyno with race fuel. Right. Because that doesn't tell you what your components did. Yeah. That tells you what the fuel did. Mm-hmm. So we always start with pump. Some cases we do have to start with race fuel because that's what's in the bike or that's all we have at the time. But we're comparing apples to apples. Yeah. And when I'm getting a little off topic on what your question was.
No, it's fine. Because you also have obviously some, maybe not, pro guys, but guys that are racing and they are going to they have a budget for race fuel. They're going to use it. They let you know, say, hey, I run Renegade or VP or whatever, and their specific type of fuel.
Right. And, sponsors and what's available to those guys. And most of the time, that's one of the misconceptions, which is where we started, is what kind of fuel do you need? What makes race fuel race fuel? It's not octane. Mm-hmm. A lot of these guys are scared to do engine modifications because they think they have to run some crazy high octane fuel. It's not the case. All of our stuff that we make will work with pump fuel.
So is there a point at which, because anytime people get a high compression piston, they always say, oh, now I have to run race gas. So Are you saying that's not the case, or there is a certain point to where you have to run it?
Depends on the components that you have working together.
Okay.
Yeah, so if you have an efficient cylinder head, you don't have to run high octane fuel.
Mm-hmm.
If you have a dead cylinder head, most of the time that thing's doing things it shouldn't be doing, and the fuel's getting puddled up in there, and it starts detonating, and you've got problems, and the only way you can really fix it is with higher octane fuel.
Oh, okay.
Yeah, so if you have everything working together, you should be down 94 octanes, 94, 93, somewhere in there. You don't have to be at 110. We actually did a pretty cool project with one of the engineering students, and I don't remember what college it was, but it was putting that theory to the test. And they called me, they're like, yeah, we're trying to prove that higher octane fuel is going to make more power. And I was like, okay. Try to kind of explain it to him a little bit, but I was like, this would be an awesome, experience for him. They came down, we tried different octane fuels, and the one that made the most power was the lowest octane. And this was on a stock motorcycle.
Right.
So, yeah, it's not always the highest octane fuel that you want to be running. It's we look for high specific gravity, high oxygen level, and the lowest octane.
And again, it goes back to application. How you're riding your bike, what the end result is.
Yeah, I mean, fuel is the cheapest horsepower you can pour into a motorcycle.
So if you're saying, but also like a super high octane fuel doesn't make the most power, then what is the application for that fuel? I mean, it exists.
Something that's super hot, or cars that are running an unbelievably high compression ratio, and as you start increasing your piston speed, or your RPM, you start building more and more pressure.
Okay.
So there are different fuels that's applicable for.
Yeah.
But not for us. We're working in a threshold of an RPM that doesn't exceed a certain number.
Right.
The higher this number exceeds, the faster these piston speeds are, the more combustion chamber, combustion you're building.
Mm-hmm.
And if it's getting hot enough and the fuel starts detonating, you need to start going up in compression.
Okay.
But for what we're doing, we don't have to worry about that.
I think wrapping it up, maybe talk a little bit about, a lot of times this whole conversation we're talking about, it really depends on what your application is. So what's the biggest difference that you see between maybe a Supercross engine and a motocross engine? Like someone that's racing outdoors versus Supercross. Like, what are the kind of differences in that, what you guys do to the head?
Well, Supercross application, we're going to be wanting to shoot for velocities.
Mm-hmm.
Airspeed. On a motocross standpoint, they're a lot higher in the RPM, higher throttle percentages. Mm-hmm. So we don't have to focus too much on airspeed, but we want to focus on making a higher horsepower for those guys because that's where they're operating at that particular RPM. Mm-hmm. On a Supercross stuff too, we talked about radiuses a little bit, I believe, and you want to have the smallest radius. You can get lost on that on the flow bench too. You can make a giant radius and you're going to gain more airflow, more CFM, but you're going to lose airspeed. Your energy is stored around that radius. So on a Supercross application, you're going to be wanting to have as smallest radius as possible without breaking a boundary layer.
And you're talking about the radius on the valves or radius, any radius?
Everywhere. Radius,
okay.
The beginning of in the airbox.
Mm-hmm.
One thing that was kind of cool was everyone was throwing the 450 air boots on the 250s.
Mm-hmm.
And it flowed more air. In theory, it would, but they weren't paying attention to the velocities. So they throw this thing on the dyno, they make a better peak horsepower, but they don't pay attention to the bottom end and mid-range numbers or the lower throttle percentages.
Mm-hmm.
So it's like, having a bigger radius like that would be cool in a motocross application because, it pulls a higher horsepower number. They're not really looking at that, mid-range power that you would be on a Supercross bike. On Supercross, these guys are coming out of these corners at a really low RPM and needing power immediately.
Mm-hmm.
You are not going to get that power immediately with a big radius. So we're shooting for velocity.
Okay.
So it all comes down to application.
Yeah. What about, I can't remember which bike it was. I think it was, putting a smaller throttle body on I think it was the the 250 KTM or something like that, or a bigger one, like what do you take into consideration? I mean, obviously you guys are working with the head and really nothing before that, right?
Mm-hmm.
Is there any time that you saw maybe throwing on a different size throttle body that worked better?
Yeah, that comes back to what are you going to be using the bike for?
Mm-hmm.
You know, a bigger throttle body, like we said at the beginning, a bigger hole is going to flow more air, but you're losing velocity.
Mm-hmm.
So you can throw a big throttle body on one of these things, and you're going to lose all your bottom end power, bottom and mid range, but you're going to gain your top. If we throw a small throttle body on there, we're going to get a more, snappy feel. We're going to get that bottom end and mid range, but we're also going to lack up top.
Makes sense.
Yeah, so it's really what these riders are wanting to get out of their engine mods. It's like, yeah, you can throw a giant throttle body on this thing, but what are you using this bike for? Bottom end, mid range, or top end power? And testing is probably the best thing that you could do. I mean, you can test this stuff and see what it does.
Is there anything else that you want to add?
No. If anyone has any questions, feel free to reach out. We're pretty open with everything. Go on our website, our email's on there, phone number, any way to contact us. So I think that's about it. It's been great.
All right. I appreciate your time, and hopefully people are coming away knowing a lot more about what's going on in their engine, how, people can change it and how you guys can change it. And, maybe this gets people thinking a little bit more about not just, I want a better bike, but what that means, because I think we've said it a million times in this conversation of really knowing what you want is more important than just saying, oh, I want it faster.
Yeah, exactly. So anyone that has questions or wants to modify their engine in a particular way, I mean, that's why we're here. So
cool.
Feel free to give us a call.
Thank you. Appreciate
No
it. Since 1968, Thor MX has elevated motocross racewear innovation to new heights. Designed and fabricated to the standards set by a long list of Supercross and motocross champions, the Thor 2020 collection features all new performance-driven racewear, boots, helmets, and more. Go to thormx.com or visit your local Parts Unlimited dealer to learn more. Next, we'd like to thank Maxxis. Maxxis Tires is proud to introduce the all-new Max Cross MX ST, a premier motocross tire tested and developed by the King, Jeremy McGrath. Available now at your local dealer. Also, we'd like to thank Chaparral. From tubes to tires, MX jerseys, gear bags, hard parts, and a huge selection of dirt bikes, Chaparral Motorsports has everything you need to keep you roosting the track or the trail. Check out chapmoto.com.